All right, guys, here we go. We're going to go over this very first problem. I'm going to do these one at a time. So you're going to get 3 videos. That way you can work a problem, look at the video, work a problem, look at the video. Okay? Excuse me. So here's the first one. Let f be a function with derivatives of all orders for which f of 2 equals 7. When n is odd, the nth derivative is 0. When n is even, the nth derivative is given by this formula. Okay, so that means that our Taylor series is only going to have even terms. If every odd derivative is 0, then every term that uses the odd derivative, which would have an x to the odd power, is going to be 0. So if we want to write out our 6th degree Taylor polynomial, okay, so I'm going to call it p sub 6. Our 0th derivative, which is our original function value at 2, is 7. Okay, our first derivative is 0. Okay, so that's going to go away. When n is 2, we get, using this formula, 2 minus 1 factorial over 3 squared, and we have times x minus 2 squared. And don't forget, because n is 2 here, you're dividing by 2 factorial. Don't forget about that. That comes from your Taylor series, definition of a Taylor series, right? Our n equals 3 term goes away. Our n equals 4 term is going to be 4 minus 1, which is 3 factorial, divided by 3 to the 4th over 4 factorial, because this is a Taylor series, x minus 2 to the 4th. Our n equals 5 term is going to go away, and our n equals 6 term is going to be, let's see, 5 factorial over 3 to the 5th, divided by 6 factorial, or times 6 factorial in the denominator, x minus 2 to the 6th. So this is our 6th degree Taylor polynomial. Now, we do not have to simplify. This is a perfectly lovely answer. If we did simplify, okay, this would become 1 over 3 squared times 2, x minus 2 squared. The 3 factorial on the top and the 4 factorial on the bottom simplify to just become a 4 on the bottom. Okay? Again, here you're in the 3/5 on the bottom, 5 factorial on top, 6 factorial on the bottom, become just a 6 on the bottom. Like I said, you don't have to simplify, but you certainly can. Okay? And it turns out it might be a good idea if we did. If we didn't do it then, we might have to do it in part B. So in part B, they say, what is the coefficient of x minus 2 to the 2n? Well, when n is 1, right, we get 1 over 3 squared times 2, right? This coefficient right here. When n is 2, that would be our x to the 4th term. We end up with 1 over 3 to the 4th times 4. When n equals 3, right, that's our x to the 6th, or actually x minus 2 to the 6th term. We get 1 over 3 to the 5th times 6. So I hope we can kind of see the pattern. Okay, our coefficient of x minus 2 to the 2n, let me write it this way, coefficient, okay, of that is going to be 1 over 3 to the 2n times 2n, right? 3 to the 4th times 4. Hey, I made a mistake up here, didn't I? Just noticed it. 3 to the 6th, this should be a 6 as well, right? Okay, oh my goodness, this should be a 6 as well. Don't be Miss Welsh. Okay, so we've answered that question, yes? By the way, part A is worth 3 points and part B is only worth 1, which leaves 5 whole big old whopping points for part C, which is our interval of convergence question. So this is where we get ratio test. Evan, this is for you. So we got the limit as n goes to infinity of what? Our n plus first term divided by our nth term. Well, what in the world, okay, is our n plus first term? What's even our nth term of this Taylor series? We didn't have to write the general term here. But I don't think it's bad because we know the coefficient of x minus 2 to the 2n. So our series then looks like x minus 2 to the 2n, and then the coefficient is 1 over 3 to the 2n times 2n. Okay? So using what we got in part B, right, we're able to write the general term, which lets us find our ratio test. Okay, so we have the limit as n approaches infinity. We got x minus 2 x minus 2 to the 2n plus 2, because we're plugging in n plus 1 for n, over 3 to the 2n plus 2 times 2n plus 2, right? Keep change flip, you got 3 to the 2n times 2n over x minus 2 to the 2n, okay? All in absolute values. So if we look at just what our 3's do, we got 3 to the 2n on top, 3 to the 2n plus 2 on the bottom, that becomes 3 squared on the bottom, okay? And then if we look at our x's, we have x minus 2 to the 2n plus 2 on top and x minus 2 to the 2n on bottom, that becomes x minus 2 squared on top. And then we still have on top a 2n and still a 2n plus 2. So we can pull whatever does not depend on n out of the limit, and we have x minus 2 squared over 3 squared times the limit as n goes to infinity of 2n over 2n plus 2. This limit equals 1, so this whole thing equals x minus 2 squared over 9, and it has to be less than 1. That's what ratio test says, right? So, whoopsie daisy. So if this has to be less than 1, then that means that x minus 2 squared has to be less than 9, which means that the absolute value of x minus 2 needs to be between 3 and negative 3. Okay? Well, actually, x minus 2. So if we unpack this a little bit, we're going to add 2 to both sides. We end up getting negative 1 is less than x is less than 5. Because they asked us for interval of convergence, we have to check the endpoints. So if I plug in negative 1, remember to my general term of my series, which was this up here, okay, I end up with negative 3 to the 2n over 3 to the 2n times 2n. But notice that term on top is always going to be positive. So I'm raising a negative to an even exponent, right? So negative 3 to the 2n is really the same as 3 to the 2n. So these cancel, and we get the series 1 over 2n, which is the harmonic series, right? Which diverges. If we plug in our other endpoint, x equals 5, we get our series 3 to the 2n over 3 to the 2n times 2n. Those definitely cancel. We get the same divergent harmonic series, so we know that our interval of convergence does not include the endpoints, negative 1 to 5 with parentheses. So I hope that you guys did really well. I hope that kind of makes sense. I'm going to make videos for the other 2 questions that I sent you so that you can watch those as well.